Welcome to Programming in Modern C++. We are in week 6 and we are going to discuss module 27. In the last module, we have introduced the notion of typecasting, implicit and explicit typecasting, basic rules for casting for the built-in types, numerical as well as pointer, and the rules for casting between non-related types and classes on a hierarchy, particularly upcast and downcast. In the module today, we will discuss about static and dynamic binding and what is polymorphic type. It follows from the casting rules, but we will have to learn about few basic notions first. This is the outline as will be available on the left. So, first we talk about type binding. And this will be a little bit of new stuff for you all, because in C when we talk of primarily of static type. That is, we say int x, and you will know that what is the type of x, that is integer. So, the compiler knows that, accordingly compiler allocates memory, accordingly compiler allows operations, the casting and so on so forth. So, everything is primarily around this. This type that you have is known as the static type, the type that you have declared an object with, and compiler sees this type. In contrast, we also have a dynamic type, which is may not be what you have declared that object for, but it is the type of the object that actually exists or refers to at the runtime. So, since it is at the runtime, the compiler does not see the dynamic type. So, here I have a very small example to illustrate this. There are two classes, A and B is derived from A specialization of that. I have a type pointer and I am doing new B, that is constructing an object of the B class type. So, if I think of the type of P, it is declared as A star, right. So, the static type of P is A star, that is, it is compiler knows that P will point to a type object, but on the hierarchy I have allowed an upcast, and actually what it points to is a B type object. So, the dynamic type of P is B star, runtime type is B star, right. So, this is the basic difference, that if the compiler knew that the static type which is pointing to an A type object, whereas in the allocation at the runtime or through assignments and so on, the type of the object that it is actually pointing to is a B type object. So, the runtime type and the compile time type differs, the dynamic type and the static type differs, and that is where a big story of polymorphism in C++ starts. So, this type assignment to a variable is known as binding. So, what I meant is deciding that what is the type of an object, that process is called binding. You are binding as if you have an object, you have multiple types, you bind it, the object, to one specific type. So, a static binding is when it binds based on the static type of the objects. So, this is all compile time. Right. So, your normal function calls, overloaded functions, overloaded operations are different examples of static binding, because the whole thing is based on the static type of the parameters and different objects involved, and the compiler knows all of them, and accordingly the compiler binds. In contrast, we have a dynamic binding in C++, when a function invocation binds to the function definition based on the dynamic type of the object. You have seen that the dynamic type of the object could be different, and so this is done at runtime. Function pointers, we have seen, is an example of dynamic type, which can be kind of simulated in C, but more explicit in C++. Virtual functions are really the dynamic binding mechanism in C++. Since static binding is done in the compiler, it is called early binding. Since dynamic binding happens at the runtime, it is called late binding. Right? So, this is the basic binding notions. So, if I quickly compare then between static and dynamic binding, then naturally the events for static binding happen at compile time and those for dynamic binding happens at runtime. All information for a call is known at compile time for static binding, but all information is not known for dynamic binding, they are known only at the runtime. As we will see, the static binding is efficient for any function call, dynamic binding is flexible, but not as efficient. Naturally, leading from that is static binding has faster execution compared to the dynamic binding. In the static binding, the actual object is not used for binding, only its type is used, whereas in dynamic binding the actual object is used, because the type of that object at the runtime is what is deciding the binding. The examples include method overloading, normal function call, overloaded functions, overloaded operators, these are all statically bound, whereas method overriding and virtual functions will be dynamically bound. Right. So, these are the basic differences. So, let us quickly look at, we have seen these kind of similar slides before. So, let us quickly take a look of a hierarchy. B is the base class, D is the derived class, B defines a function f, D defines another function g. So, if I now have two objects B and D, then naturally B dot f will call the function in the class B, D dot f will call the function in the class B again, because it has inherited it, and naturally D dot g will call the function that you have added. If I use overriding, I have a function f in B, and in the derived class I have overridden the function f. So, if I do B dot f, it will be, this will call the B class function. If I do D dot f, then this will call the D class function, because I have overridden it. Right. So, when I override, then I have actually lost the original function that I had in the base class, that has got masked. Right. There is no way to call that function anymore, right, unless I explicitly put the scope and write that. So, if I want to inherit a function from my base class and just overload it, I will not be able to do that, because the moment I overload, that will hide the previous function. Let us see an example. We will come to that example. Now, this is from module 22, just I am asking you to go and revisit that. G and f and g are in base class, they are inherited in the derived class, and naturally everything that you call from B or D is in the base class function. Here you have B and f and g in the base class, you have overridden f here, same signature, you have overloaded f here, you have inherited G just like that, did not do anything with it and introduced a new function. So, when you call from B, it is all B class objects. When you call from F from D, you get the overloaded overridden F3, I am sorry, overridden F3, which is the D class function, and G of course is just inherited. So, you will get to see the G of the B class, and if you call the overloaded F, then naturally you will get the F in the D class and so on, right. So, you have already seen that. This is just a recapitulation reminder. Now, we were talking about what happens if I inherit a function from the base class and then override it or want to overload it. Say for example, I have a class A with a function f and B is inherited from that. Now, if I just do f int, it will overload the function f in B. So, what you cannot see is, what you cannot see here is there is a function f available here which comes from the scope of B. So, when you put a different signature for f, you are actually overloading that function. As you do that, you will not be able to call the original function. You will with B, an object B, you will not be able to call B dot f, because it does not exist, you have already hidden it, masked it. So, to avoid this problem, what is introduced is a new use of the using keyword. You already have seen that in terms of namespace. It is a different context where we are doing using. So, it says using A colon colon f. What does it mean? It means that do preserve the function f from the base class and treat this as a overload. So, when you want to do that, then you do this using keyword and give the fully specialized, fully qualified name of the function that you want to use from your parent context. So, with that you will now be able to call your overloaded function, and as you do B dot f, you actually call the function from the base class A, right. So, this is how you can make the overridden functions or overloaded functions from the base class also available to your class if you need. So, this was about static binding. Now, let us talk about dynamic binding, which is, so this is B is a D which overrides the function, I am sorry, D is a B, that is D is a derived class, B is the base class, and I am overriding the function f. I have overwritten it here, and when I make the call, naturally just look at what I am doing. There are two objects B and D and a B type pointer, which is a base type pointer. Now, if I assign the address of the base class object and invoke, it will invoke B colon colon f, no issues. If I assign the derived class address of the derived class object to the base class pointer and then try to call f, it will still call the base class function, because this is done by the compiler at the static time, at the compile time. So, the compiler knows in P here, in resolving P here, compiler knows that it is of B type. So, it binds with this function, it does not bind with this function, and but probably D being a object of the class D, you probably would have wanted to use the other function in the class D. It is of course your choice. When this happens, this is called static binding. Now, how can we change this scenario? There is a very simple way to change this. All that you need to do is to put a keyword virtual before the function signature, everything else is same. instances, this up to this point there is no difference. But if you do this, p pointer p you have set to the address of a D object and you do p pointer f, it does not call b colon colon f. Instead, it calls D colon colon f. That is, the compiler does not resolve that since p is a class B base class type pointer. So, f that is trying to do will have to come from the base class. Compiler does not resolve that. Compiler does some mechanism which we will subsequently talk of, which allows that at the runtime when the pointer actually is pointing to an object which is a derived class object. Since it is pointing to a derived class object, it will call the function overridden function in the derived class, not of the base class, and this is what is dynamic binding. So, such functions that you write is known as virtual function, right? And that is the backbone of dynamic binding, polymorphism in C++. So, just to compare how do they look like in terms of static and dynamic binding, I have a function f here which is overridden in the derived class which is non-virtual, and I have a g which is virtual, right. So, you can do this, you can have a pointer p b which holds the base class object, pointer p d which holds the derived class object, but p d is of type base class. So, there is an upcast involved here. Similarly, just to illustrate the same mechanism can be done for reference, I have also created two references. One is a reference to the object B and the other is a reference to object D, but the reference is of type B, base class type, again an upcast. Now, if I call the functions with the object directly, then they get called according to their type. So, calls from B goes to B class function, calls from D go to D class function, there is no surprise in that. Now, suppose I call this functions using pointer p b pointer f. Now, what is f? F is a non-virtual function. So, it is statically bound. So, which function it will call is decided by the type of p b, which is the base class. So, it calls b colon colon f, we have a static binding. But what happens if I call p b pointer g? Now, g is a virtual function. So, it will be dynamically bound. So, it depends on what p b is pointing to. What p b is pointing to? P b is pointing to a B class object. So, since p b is pointing to a B class object at the runtime, it will invoke the B class function B colon colon f, but this is happening through dynamic binding. Now, take a look as to when we have p d. What is p d? P d is of type base class, but it is actually pointing to a derived class object. So, when it does that for a non-virtual function, you have static binding. So, it is decided by the type of p d and B colon colon f is called. But when you call the virtual function through p d, though p d is of type base class, but it is actually pointing to a derived class object. So, it resolves at the runtime that it will call the g function in the derived class of which the object is currently there. So, this is the illustration of the dynamic binding. Similar behavior will be seen also for the references. So, this references and these calls, if you tally, you will see exactly the same mechanism. So, I mean we get to see that dynamic binding is possible with only with virtual functions that are overridden, and if you are making the access to the function through a pointer or through a reference. Otherwise, it is static binding. If you are dealing with non-virtual functions, then it is always statically bound. If you are invoking through the object directly, it is always statically bound, but only with pointers and with references and virtual functions you will have this dynamic binding behavior. This is a very, again, a very profound one slide summary of the difference. So, please mark this slide and keep on referring to it whenever you have some confusion. Now, this dynamic binding leads to polymorphic and non-polymorphic type, notions of polymorphic and non-polymorphic type. Polymorphic, again I would reiterate, means that something that can multiply morph or multiply interpreted. Poly is many, morph is change. So, same thing, but can be seen in multiple ways. So, dynamic binding is basically giving us the polymorphism. So, as we have noted, dynamic binding is possible only for pointer and reference data types and for member functions that are declared as virtual in the base class. Such member functions are called virtual functions. So, it is a access by pointer or reference and available for virtual functions only. If a member function is declared as virtual, it can be overridden in the derived class, right, as you override non-virtual functions as well, but you can do the same thing for virtual functions. If a member function is not virtual and it is redefined in the derived class, then the later definition hides the former one. We have already seen that, right? How by overriding you actually lose the earlier definition, but unless you explicitly do using and want to use it, but there are complications if you try to do that often. But in dynamic binding, that is the mechanism that you are overriding, but all of the functions from the base to the current class, all of these overridden functions that are virtual will be available based on the actual type of the object that is being used in the invocation of the function through the pointer or a reference. So, given all these, any class which contains a virtual member function, at least one, it may be many, but if a class contains at least one virtual member function, which could be either by definition that it is declared it as virtual, or it has got by inheritance because its parent had a virtual function and being a specialization it has inherited from the parent. Virtual functions are always inherited as virtual functions. Then such a class or such a type is known as polymorphic. So, it will lead to dynamic binding for that class. So, a hierarchy may be polymorphic or it may be non-polymorphic. Again, I may not have any virtual function from at the base, so that the whole hierarchy is non-polymorphic. The reality is, well, so far whatever we have been discussing about the hierarchy were naturally non-polymorphic, but in the actual practice a non-polymorphic inheritance hierarchy has little value. It is used only for certain specific cases, but most often you will see that the real power of object oriented programming in C++ will come when you have polymorphic types. That is, you have a hierarchy where you have say a root and you have inheritance. There could be inheritance of. So, this is child 1, this is child 2, this is child 3 classes, this is grandchild 1, this is grandchild 2, this is grandchild 3, this is grandchild 4 and so on. Now, if I have a virtual function here, one or more virtual functions, those will all be available all through this hierarchy, right. So, that is what is the meaning of a polymorphic type or a polymorphic hierarchy, which will be the mainstay of object oriented design for C++. So, that is just a quick set of illustrations. Here is a class A. So, this is the hierarchy diagram. Class A, which is a base class, which has one virtual function G. F and H are non-virtual. Then it specializes into B, where F continues to be non-virtual, G is virtual. You would ask, why is G virtual? You have not written virtual here. The rule is, once a function is virtual in a class, then in all its derived classes it is virtual. You cannot change that. But you can do the reverse. For example, in here H is non-virtual, but what I have done while overriding, I have made it virtual. So, in class A H is non-virtual, but in class B H is virtual. So, B becomes a new root for the subsequent classes, where H will be treated as a virtual function. Now, I have C, which is overriding all three of them. Now, F is non-virtual because it was non-virtual. G and H both have become virtual in B. So, it will be virtual in C as well. So, with that, if I create a C object and put the address to a B type pointer and have another pointer P, where I have upcast this pointer. So, P is a type pointer, Q is a B type pointer, and the actual object both of them are pointing to is a C type object. Okay. So, what will happen if I do P pointer F? What is F? F is a non-virtual function. So, what will it do? It will decide by the type of the pointer. P is A type. So, this is what you get, A colon colon F. What if you do P pointer G? P G is a virtual function, right, and P is currently pointing to a C type object, right. G is a virtual function in class A, P is of class A. So, in class A it checks whether this function is virtual or non-virtual, decides whether it will be statically bound or dynamically bound. It decided for F earlier, now it is deciding for G, it finds that it is virtual. So, it is dynamically bound. So, it does not decide on the based on the type of P, it decides based on the type of the object it is actually pointing to, which is C. So, what it calls? It calls the G function of class C. What happens when I do P pointer H? H is non-virtual. So, it has to be statically bound. So, it will call A colon colon H. Right. Now, let us think about the pointer Q. If I do Q pointer F, Q is of type B, right. So, it will look for this B class for resolving whether it should statically bind or it should dynamically bind. So, it finds that F is non-virtual here, it has not inherited virtualness from the parent either. So, it will bind by the type of Q, the type of the pointer. So, type of the pointer is B, B star. So, it calls B colon colon F. Now, if I look at G, what will happen? G is not explicitly written here, but is inherited the virtual function property from its parent. So, it is a virtual function. So, it will not be statically bound, it will be bound to the current type of the object Q is pointing to, which is a C type object. Therefore, it calls the G function of the class C. Finally, it is Q pointer H, which was not inherited as virtual, but has been defined as virtual in the class B. So, Q will treat this as a virtual function now. So, Q will not, this binding the compiler will not generate based on the type of Q. If it would have done that, it would have called the function B colon colon H, but it will not do that because the actual object is of type C and this is a case of dynamic binding. So, it will call the function H of class C, C colon colon H. So, this is again a one slide summary rules I would say that you can use to quickly refer to any time you have an issue in understanding this. The example is worked out with pointers. The same example can be done with reference also. You should run this, check this out, make changes. The basic idea is once a virtual, downwards it is always virtual. But I can take a non-virtual function and make it virtual in a class, but I cannot do the reverse. The virtualness cannot be erased, but it can be added. And when I resolve for the binding, the pointer of the reference looks at the class of the type it is defined by. So, a pointer to A will always look for the status of the functions defined in A, whether they are virtual, whether they are non-virtual, and based on that for virtual functions they will do, it will do a dynamic binding, for non-virtual function it will do a static binding. If you understand this rule, then the whole of polymorphism, or so to say handling of polymorphic hierarchy in C++, which is the core of object oriented design in C++, will be like a easy cake for you. So, here we have discussed about static and dynamic binding, and we have just introduced the polymorphic type. We will talk more about that in the coming modules. Thank you very much for your attention, and we will meet in the next module.